All right, it's time for some aromatic chemistry. And of course, in organic chemistry, we're not talking about things that smell very nice. What we're talking about is reactions on benzene. And for those of you who are following our course here at Stellenbosch University, in our second year, right now at the end of our semester, this is the first time that we are looking at reactions on benzene rings. Up until now, we've basically told you don't touch them. Anything that we throw at them is not going to do any reaction. And now it's time to learn about how we're going to do reactions on a benzene ring. And so everything that we said to you so far has been like 100% true. The reagents that we have given to you don't react at all with benzene rings, because benzene rings are extremely stable. This principle of aromaticity, we draw our benzene ring like this. It looks like a cyclohexatriene. It's not. These double bonds are all delocalized, and we also know that the reason for it, Huckel's rule. There's a special stability that's obtained with these things, but the reactions of benzene rings is a nice one to follow after we have done our electrophilic addition to alkenes. So because there is some similarities to this. So if this was just a cyclohexene, so it just didn't have two of the external, it had a double bond, and if we added bromine to it, we learned in our reactions that to alkenes that bromine is an extremely powerful electrophile, and it really is. I've mentioned to you that to use bromine is a horrible reagent to work with it. It will even start to degrade the stainless steel needles that you would use to kind of suck it up as a liquid. So it's very powerful. But you stick benzene and bromine together, you stir them around, and absolutely nothing will happen. We can get bromine to react with benzene though, but what we do need to do is we need to put on a very a powerful Lewis acid. And aluminium trichloride is one of the most common ones. There are others that could be used, but we just need to remember that a powerful Lewis acid is important to react with something which is so unreactive like benzene. And when that happens, we can get the benzene ring to add a single bromine atom to it, and so we get bromobenzene being formed. Now, this, of course, is much more useful. Once we've got a bromine onto an aromatic ring like this, you can think of things that we could do. For instance, we could treat it with butyl lithium, so we get a lithium intermediate over here, which could then act as a nucleophile. Just the same way, we could actually just you do a Grignard reaction, so add magnesium to form the Grignard reagent, and it'd be able to do a reaction. So it's really useful to be able to do something like this. But let's just talk about how this happens, and then I'm just going to show you some other reagents that basically do exactly the same sort of thing. Not putting bromine on, but powerful electrophiles that add something else on there. So the key here is the aluminium trichloride. So normally, what we normally have is we understand that bromine is a powerful electrophile because although it's balanced, we just need a small kind of push of electron density, and it's going to throw the electrons towards, because Br is a really good leaving group, and it makes the one bromine very electrophilic. Of course, it could happen either way. But it's the interaction of the Lewis acid, which is so powerful itself. Aluminium has this empty p orbital, and the lone pairs of any one of the bromines, we choose this one, add to the aluminium. And when that happens, we basically activate this even more as a leaving group. So we're actually just pulling it away even stronger. That super activates this other bromine over here to become an even more powerful electrophile than it ever was before. And we can draw the reaction of the benzene ring, one of those alkenes. I don't like using that term. Rather, one of the electrons in the pi bond over there. Again, kind of a little bit bad to use that term because this is an aromatic system. It's not just an alkene. It's not just a single pi bond there, but like a whole system. But the HOMO of the benzene is able to add to the bromine and kick off like that. And so if we draw this out, let's just look at what we get as an intermediate. So when we get this intermediate over here, what's happened is we have now destroyed the aromaticity of this ring. We've added a bromine on. We've now got this carbocation. Now, for those of you, as you're more familiar with carbocations now, you might look at it and say, but hang on a second, this carbocation is actually stabilized because we've got these double bonds over here. So, that double bond can go across like that. So we can get this nice resonance form over here. We draw that out. And we say, but look, the positive charge can be stabilized again because this pi bond could move in and we get a carbocation over there. So you might look at this and say, but this is fine. Why is this such a big problem over here? We can get 3 different places where the carbocation can be stabilized. And so, this should be a really easy thing to do. It's a relatively stable carbocation. But carbocations, A, are not very stable, but B, this structure over here, 6-membered ring, is absolutely desperately wanting to get back to being aromatic. It is screaming to be an aromatic system. And because of that, something can leave. In this case, this proton suddenly becomes very acidic. This is almost like our E1 elimination type reactions, and it can be given back in to give the aromatic system like that to re-aromatize. What picks up this proton over here? Well, it could be this Br minus that is over there, or one of these chlorines. So in other words, what we're going to generate is some acid. So in this case, what we left behind with is HBr plus the aluminium trichloride is effectively reformed. So this means that the aluminium trichloride is effectively a catalyst. We don't have to have stoichiometric amounts of it present, but we do need to have stoichiometric amounts of the bromine. And so bromine is our entry point into reactions on benzene rings. Now I want to talk about some of the other important ones that take place and show you how they work. All right. The next reaction I want to look at is nitration. So next to bromination is of course fantastic because it puts a handle onto an aromatic ring which we can then manipulate with later on. Next to bromination, nitration would then be my next most favorite type of reaction for functionalizing an aromatic ring. We've taken something, a benzene, which is very boring. There's nothing on there, and we put a nitro group on it like this over here. Now, why do I say that this is such an important group to put on? A nitro group, for instance, that's the name of the functional group, is not one that you are perhaps very familiar with, but the key here is that we can very easily reduce this down to an amine, and this is something that you should know. And the reagent that we use to do this is just hydrogen with palladium on carbon. There are many different ways of doing that, but it's just easy to remember just one method that works very, very nicely. This is this method over here. We can reduce a nitro group to an amine. And amine is an incredibly useful functional group. It's a weak but pleasant enough nucleophile that can do other reactions and that sort of thing. So amines are excellent functional groups. So how do we put the nitro group on? Well, we need a very powerful nitrating reagent, and the nitrating reagent is made by mixing 2 extremely strong acids and nasty acids to work with. So we use nitric acid and sulfuric acid. So these 2 can be added together to form the nitrating agent. You've done this as a prac, for those of you in my second year course. So it is something, even though these are very strong acids and very powerful, they are okay for undergraduate students to work with very carefully. I remember we had to do this at low temperatures. So the nitrating of this works by generating a nitronium, and that is made this way. So let's look at nitric acid. So nitric acid is in. And what happens is that we need the sulfuric acid to protonate because it's such a strong acid. we're going to protonate this OH over here in order to make it a good leaving group. I know the tendency might be to see, oh, but there's a minus here. I want to protonate that. Just remember that this minus over here is delocalized over the 2 oxygens. So this could kick in over here and kick out over there. So it's not actually as O minus as you would like to see. And so this oxygen over here will get protonated. I should have drawn the bond. Obviously that bond would break and go onto there. This is a strong acid and it can do that. So we get this. We have now effectively made a very good leaving group in the form of water. Let's get our charges on here. And now what can happen is this can kick in like this and kick out the water. And what we get is our nitronium. And this NO2 plus is an extremely powerful electrophile. And in the same way as we did earlier on with the bromine, we can do exactly the same sort of thing. The pi bond will add to that, kicks out over there, and we generate the intermediate. All right, there's the nitro group on there. Just remember, NO2 is this is exactly what it looks like. It's a nitrogen with a double bond to oxygen and a single bond to oxygen, positive nitrogen, negative on the oxygen. And of course, this is you can draw it out. This is a delocalized form, one of the canonical forms. You can kick that in, kick out, and we get an O minus over there. And all that needs to happen at this point over here is we lose a proton, kicks back in, and that gives us our product over there. So nitration, and you do need to know this mechanism. Nitration is generated by having strong acid, nitric acid and sulfuric acid, protonation of the OH part of nitric acid to make it into a good leaving group, and we get the nitronium intermediate. Nitration, extremely important reaction for functionalizing aromatic rings. All right, our next reaction they're going to look at is sulfonation. And this is making a sulfonic acid. So this is very close. What I've shown here is benzene going to a sulfonic acid. This is very close to if we put a methyl group over here, what we would have is paratoluene sulfonic acid. And so this is one way of doing this. This is, to be honest, I'm going to say it's not common, but that's only my fault because I only ever did this once. Ever needed to use a reaction like this. But it isn't one that you see pop up as much as sort of the bromination or nitration of aromatic rings. This is really easy because we can just use concentrated sulfuric acid. It really does need to be essentially pure sulfuric acid to do this. And we do need to heat this up as well in order for this to occur. So what happens is the sulfuric acid reacts with itself. So we're going to draw out the 2 molecules of it. So what happens is very much like we protonated the nitric acid to make a good leaving group. We need to make one of these OHs into a good leaving group. And that's what we're going to do. So what we do here is that this OH, I choose anyone, but I'm choosing this OH over here, is going to pick up a proton and get protonated. What happens then is it makes that into a good leaving group, namely water. And so this can leave, and I've kind of drawn the arrows back to front there because the lone pair of this oxygen over here can kick in to kick out the water. And what we're left with is essentially a protonated form of sulfur trioxide. This sulfur atom now is an extremely powerful electrophile. So we can actually change it now into pink. And so we can go through the process. I'm not going to do that here. You should be able to go. It's all the same arrow pushes, but the pi bond will add to the sulfur like that. Kick that out, and we get the sulfonation of an aromatic ring. The last reaction that I want to do is known as the Friedel-Crafts reaction. Now, actually, it's 2 separate reactions. One is very useful, and the other one is not so useful. So the not so useful one, I'm going to do that first. Essentially, this reaction is using a very powerful electrophile that you have already seen. and that is a carbocation. A carbocation is extremely powerful electrophile and will react with a benzene ring. The problem is that carbocations are not very stable. And so for all intents and purposes, generating a carbocation from, say, something like this is going to be a little bit easier, but we need to pull this chlorine off. In order to generate a carbocation over here, we somehow need to really rip that chlorine atom off. And the way to do that is to, again, add a very powerful Lewis acid. So aluminium trichloride shows its head again. And I'm just keeping the same Lewis acid just so that it's easier to kind of remember. It's a good one for you to remember. But at the same time, if you get asked a question that looks like this, but there's a different Lewis acid here, maybe it was iron, maybe it was some other metal, the key thing is just to remember that it's the same sort of thing that must be occurring, even if you haven't seen that particular example of a Lewis acid. But if you're asked to draw out and you've got to give some reagent, just choose the aluminium trichloride just as a default, because that's fine and will almost certainly work. So what happens here is that I'll draw the product. It's going to form this carbocation, and we're going to obviously put a T-butyl group on over there. So this carbon is the one that's going to become the carbocation, and that's the one over there. Now, this obviously can't be a straight substitution reaction. That's impossible. This is too weak a nucleophile, and so it has to be via ripping off this chlorine group first. And that's what the aluminium trichloride will do. So the first step is lone pairs of electrons and act as a nucleophile. This is why I always say lone pairs are nucleophilic. Even though this might be very weakly nucleophilic on a halogen, they are nucleophilic because this is such a powerful electrophile, this Lewis acid over there. And so it pulls the electrons to that. And when it does that, it rips that off from there, generating our carbocation intermediate. And tertiary carbocations are okay for this. The minute you start doing this on a secondary or primary carbocation, I don't want to go into too much detail here because you can get them to work in certain circumstances, but the problem is those carbocations have tendencies to rearrange. And so this is why I've said this example over here is not really is probably like the only one that is useful, just as simple as it is over here. So then we can just react with our pi bond. It adds on over there, and we get the same sort of intermediates. We first draw the cationic intermediate, and then it eliminates again to give our aromatic ring. So this one over here is the Friedel-Crafts. Sometimes we just abbreviate it as FC. Please don't do that in an exam. Please write out Friedel-Crafts. But this would have been the Friedel-Crafts alkylation. Said to you in the beginning that there's actually a far more robust and useful version of the Friedel-Crafts reaction, and that is the Friedel-Crafts acylation. And that looks like this. So in the Friedel-Crafts acylation, what we're doing is we're putting on this acyl group of, and it could be other groups over there, so it's no longer technically an acyl, but it's still called an acylation. So it's from acetic acid, but you could have other long chains going along. So again, what happens is the aluminium trichloride pulls off the chlorine. The advantage here is, although we're forming a carbocation which is not normally stabilized there, the intermediate is slightly stabilized by the oxygen's lone pair. So let's look at what happens over here. We'll do it stepwise. The chlorine is going to donate its bonds to the aluminium, which is going to pull away that bond over there, generating the acylinium, which looks like that. But this thing is resonance stabilized because we've got these lone pairs which can kick in to stabilize that positive charge. And now what happens, but just look at the structure. Notice that what's happened here is that this carbon now is sp hybridized. It's going to be linear, and this is the acylinium intermediate. And typically when we do these mechanisms, we normally operate on using this intermediate to show the mechanism, but you can use this one as well. I won't penalize you for that, and we can then add with our benzene ring, boom, onto it, and that will generate a cationic intermediate like everything else, which then needs to go eliminate and form our aromatic ring. All right, so these are the main reactions that we can do on aromatic rings. There are a couple of other ones, but these are the most important ones for our course, the 5 ones. So we've looked at bromination, we've looked at nitration, we've looked at sulfonation, and we've looked at the 2 Friedel-Crafts reactions. For the Friedel-Crafts reactions, alkylation and acylation, these are very useful reactions in terms of forming a carbon bond onto an aromatic ring. Just be aware that in alkylation, we're just going to keep it, and I won't take that any further in this course. We're just going to keep it as a tertiary carbocation like this that reacts. And in terms of acylation, it could be other things over there. So if we wanted to, right now, we can just put an R over there, because it could be some other things, although typically it's, the classic example is in the acid chloride. So it could have been an R group, which of course would have been R there as well. And this is a far more useful reaction, mainly because the carbocation that forms over here is stabilized via forming this acylinium because of the oxygen's lone pairs. It's less chance of rearrangements occurring, and so it's a little bit more of a robust reaction. So now that we have done that, our next step is going to have to be an understanding about how benzene can actually be modified to either react a little bit more, to become more reactive, and how sometimes a substitution or something that's on a benzene ring actually deactivates a benzene ring. And we're going to have to start to look at where these reactions are occurring. This one was all these examples were very boring. We started with plain benzene. But where we need to move into the future now is to think about what happens if there was already a substituent over here, something simple like a methyl group, for instance. It's a bit boring, but if there's a methyl group over here where this reacts, there's 5 different positions, and we need to kind of figure out and learn where the favored positions are for the different reactions, and we'll be doing that in the next lecture.